Hello, and welcome to Group 91's project video for the Star Search simulation system. This project was completed by Andrew Fleer, Ryan Truen, James Traveri, and Kyle Becker as part of the CS6310 Software Architecture and Design course at Georgia Tech. The Star Search simulation system is a simulation system that focuses on small, semi-autonomous drones for the exploration of remote areas of space. These drones are semi-autonomous in that they can occasionally receive commands directly from their human controllers. However, there are also times when communicating with the drones is not possible. Because of that, the drones must be able to continue their exploration activities using only their own internal capabilities. The simulation system allows the user to test a variety of drone capabilities and strategies. This is achieved by reading a scenario file that includes the characteristics of the region of space that will be explored, the capabilities of the drones that will be exploring that region, and other details about the simulation run. We chose to add 3 additional features that we believe would be useful to the client. The concept of fuel, which makes our simulation system slightly more realistic as drones now have a finite source of energy. The addition of comets, which creates a more realistic and challenging scenario as these obstacles are mobile. And a graphical user interface that allows the client to monitor the state of the simulation system. Let's take a look at how to build the application. Assuming you have access to the source code, the first thing you want to do is build the jar file using Maven. Execute the mvn package command to begin building the jar file. Once the jar file has been created, you are ready to run the application. Our application is built using Java and JavaFX, so you need to include the JavaFX SDK path, as well as the JavaFX modules, javafx.fxml, javafx.control, and javafx.graphics as arguments by executing the following command, noting that the location of our JavaFX SDK may be different than yours. Now that we have a running application, let's take a look at the components. Starting at the top of the left pane is the file loading section. The file loading section contains the scenario file text field and a button for loading the file into local memory. Beneath the file loading section is the scenario section. The scenario section contains relevant information about the scenario loaded into memory. File name displays the name of the file loaded into memory. Grid height and grid width display the integers corresponding with the map size. Drone count, sun count, and comet count provide the initial counts of drones, suns, and comets and are unaffected by the simulation. Beneath the scenario section is the Sim Manager section. The Sim Manager section contains information relative to the simulation. The state of the simulation manager, the number of turns that have been completed, the overall space region, which is defined by the grid height times the grid width, the initially explorable spaces, which is a count of all the non-sun or comet spaces, the spaces explored, which is a count of the spaces that are either empty or contain a drone, explored, which displays a percentage of the map that has been explored, a remaining turn label that provides the total number of turns remaining, and lastly, the drone label, which provides the user with feedback as to which actor is next. Beneath the Sim Manager section is the drone section. The drone section contains a combo box that displays all of the drones loaded into memory. Once loaded, the attributes relevant to the drone class will be updated. These attributes include the state of the drone, which is either active or crashed, the strategy, which is either random or intelligent, the drone's position, given as X and Y location coordinates, the drone's orientation, which displays the cardinal direction, lastly, a fuel indicator, which provides a quantity of the remaining fuel in the drone. Beneath the drone section is the playback section. In the playback section, you will find 3 buttons: Play Next, Fast Forward, and Stop. These buttons will enable and disable as applicable to the simulation state. For instance, right now they are disabled because there is no file loaded into memory. However, once a file is loaded, the buttons will be enabled, and then disabled again after the completion of the simulation. The Play Next button advances one action at a time until a stop condition occurs. A stop condition occurs when either all of the drones have perished, there are no more explorable spaces, or the simulation has reached the maximum number of turns. The Stop button stops the simulation before receiving a stop condition and reports the statistics of the simulation at that instance. And finally, a Fast Forward button that allows the simulation to continue without user interaction until one of the stop conditions occurs. Moving directly to the right is the message box. The message box provides feedback on drone actions, simulation manager responses, and exceptions that get thrown throughout the simulation. Above the message box is the space viewport, which will include a graphical representation of the space map. Let's go ahead and load a file. By default, the scenario file text field is populated with scenario0.csv. Scenario0.csv is one of the pre-populated scenario files located in the resources/scenario directory. To load the file into memory, click the Load File button. You can tell the file loaded successfully by looking at the message box. Notice that when the file was loaded, all other attributes were updated as well. The left pane now contains both data and active buttons. The message box contains a message stating a successful load, and most notably, the space is now visible. Let's step through one complete turn to see what happens. To begin advancing through the actions, we will need to click the Play Next button. After pressing the button, you can see the action that was performed by the actor by looking at the message box, and even the graphical representation if the action resulted in a physical change. After clicking Play Next a few times, go ahead and finish off the simulation by clicking Fast Forward. You can tell the simulation is complete by checking the Sim State label on the left. Lastly, let's create a scenario file of our own. Let's start with scenario0.csv as a template. Open up the scenario file in your favorite text editor, and let's go through the lines. Line 1 is space width and accepts values between 1 and 20. Line 2 is space height and accepts values between 1 and 15. Line 3 is the number of drones and accepts values between 1 and 10. For each drone, you will have a configuration line. Within this line, you will have the X position, Y position, orientation, and the strategy, separated by commas. For the strategy, the number can be either a 0 or a 1. A 0 being a random strategy, and 1 being the intelligent strategy. After the drone configuration lines, the next line will be the number of suns, which accepts a value between 0 and 50% of the space region, with the space region being defined as the space width times the space height. For each sun, you will have a configuration line that contains the X position and the Y position, comma separated. After the configuration of the suns, you will have the number of turns allowed, which accepts a value between 1 and 200. The next line contains the number of comets, which accepts a value between 0 and 50% of the number of drones, followed by a configuration line for each comet that takes an X position, a Y position, and an orientation. Now save this file in the resources/scenario directory, and this file can now be executed from the application. Thanks for watching.